Okay, so today we'll get to the part 2 or chapter 5. Okay, so we'll be talking about linear transformation for vectors and also the eigenvalues and eigenvectors for a transformation matrix. Okay. So first of all, so what do I mean by transformation? Okay, so more specifically, I'm talking about transformations of vectors. Okay, so and suppose, right, so I have a vector v, and then I do this transformation, which I denote it by this t of v, and then after this transformation, I get another vector out, this v prime. Okay, so this t of v, right, so this t itself, so acts like a function. Okay, so essentially, so it takes an input, right, but this time the input is not the number, but instead it takes a vector as an input, right? And then it spit out another vector for you, right? So that's v prime. So the input and output vectors. Okay, so previously, if you learn functions, then the input is a number, output is a number. Okay. And also, okay, so the vectors that we can think of usually can be a vector in two-dimensional space, right? So, or it can be a vector in three-dimensional space, right? So, and in general, okay, so the input vectors and the output vector do not necessarily have to have the same live in the same dimensional space. So that means you can input a vector that live in a three-dimensional space, and then it can output a vector that is live in the two-dimensional space after transformation. Okay. It really depends on what kind of transformations that you are talking about. Right. So, but anyway, in our case, so we're focusing on we either have a vector living in a two-dimensional space, and then after transformation is also still in the two-dimensional space. So this is a case that we'll talk about a lot. Okay, so and the second case is that we either have vectors that live in a three-dimensional space, and after transformation is still live in a three-dimensional space. Okay. So just one thing to remind you, I think last time I already used this column matrix to represent a vector, right? So in the last part of this chapter, is that just again give you a reminder is that if I consider a position vector of a point, right? So v, right? So usually we write it this way. Right, so if you talk about position vector of a point, and this x and y, right, so would be the x and y coordinates of your point. So and here in this chapter, we'll use this representation, right? So write it as a column matrix. Okay, so the first entry, right, so tells you the magnitude of the x component of your vector, right? And then the second entry tells you the y component, right? The magnitude of the y component of your vector. Okay. So then that means if you just have x hat itself, right? So then the how do I represent it? So then it will just be 1, 0. Okay. And if I just have the y hat, so I'll just represent it as 0, 1. Okay. So, and the way that I represent this is also known as a column vector. Okay, so this the reason why we want this representation is that later we'll be making products, right, between this matrix and vector. So that's why I write this vector in this notation here. Okay. So then here, right, so you can see that this is an example of transformation, right? So this blue vector v is my original vector. Right, so after some transformation, I get this red dash vector v prime. So you can see that in general, a transformation can change the magnitude of the vector, okay, and it can also change the direction of the vector. Okay. Again, it depends on what kind of transformation we are talking about. Okay. So in fact, here we'll focus on the so-called linear transformations. Okay. And linear transformations have the following properties: is that if I transform sum of these two vectors, okay, so v1 plus v2, so that would be the same as transforming the two vectors individually and then sum them up. Okay. So this is a property of linear transformation. So another property is that if I'm going to transform this vector, which has been multiplied by a scalar factor c, then it would be the same as transforming the vector v itself first, and then multiplied it by that scalar factor c. Okay. So then from these two properties, you'll be able to conclude that if I have n vectors, if I take a linear combinations of n vectors, so like this, right? So scalar a1 times v1, okay, plus scalar a2 times v2, and so on. So if you consider the transformation of this vector, okay, so then it would tells you that it's the same as taking a1 times t v1 plus a2 times t v2 plus all the way to an times t vn, right? Right, so if you have a linear transformation, right, so this is what has to be true, okay? So in fact, any linear transformation, so for the column vector, so can be represented by a matrix, right? So, okay, provided that we have already represented our vectors as a column vector. Okay. And if you are going to transform a vector which originally lived in the nth dimensional space to another vector which lived in the m dimensional space, then you will have that linear transformation represented by an m by n matrix. Okay. As I said, we'll just focus on from two-dimensional space to two-dimensional space. Then in this case, right, so then the transformation, any linear transformation can be represented by this matrix here, a 2 by 2 matrix. Right, so I take column vector and then do this matrix vector product, and then I'll get to the transformed vector. Okay. So then now the question is how do we construct the transformation matrix here? So any vector, okay, in the two-dimensional space can be expressed like this. Okay, so it's basically because, as I told you, this 1, 0 really means x hat, right? This 0, 1 really means y hat. So that's why the vector can be written in this way. Okay. So then if I want to transform this vector v, right, so for any xy, then it will be the same as transforming this vector, right? Transforming this vector here. And as I just told you, right, because of the property of linear transformation, it could be treated as a sum of these two transformed vectors. Okay. So that means if I transform this 1, 0 vector, right, so multiplied by x, and then plus the transform vector for this 0, 1 multiplied by y. So that means if I tell you the transformation for 1, 0 and 0, 1, then you can tell me the transformation for any vector. I just need to tell you this t10 and t01. Right, so in matrix form, right, so this t of v can be written as this matrix vector product. Right? And because here I have sum of two vectors, so I can just treat it as a sum of two terms, right? So the matrix vector product for this 1, 0 and this matrix vector product for this 0, 1. So, and that means if I just take the transformation for this 1, 0, right? So you do this product, and then you find that this is A11 and A21. And similarly, if I just take the transformation for this 0, 1, you'll find that this is A12 and A22. So that means to construct a transformation matrix, you can just focus on two special cases. The first case is how does this 1, 0 transform? Right. So after you know that, you can write your transform vector for 1, 0 as the first column of your transformation matrix A. So similarly, right? So you look at the behavior of the transformation for 0, 1. So if you know that 0, 1 transform to some vector, then you just treat that as the second column of your transformation matrix. So this is how you construct a transformation matrix. Okay. So that means is that if you know that you are dealing with a linear transformation, right? So and you know that the transformation behavior for 1, 0 and the transformation behavior for 0, 1, then you can immediately write down your transformation matrix. So again, this is a special case, right? From two-dimensional space to two-dimensional space. Okay. So now, right? So although we are not going to do this general case a lot, but I just want to also tell you that in general, right? So if you are taking an n-dimensional vector, right? So do transformation, and then it becomes a vector, another vector in the m-dimensional space. So then that transformation matrix will look like an m by n matrix. Right? So, but the idea of constructing this matrix is really the same, right? So is that this time you cannot just consider 1, 0 and 0, 1, right? So instead you need to consider the n basis vectors in this n-dimensional space. So the basis vector in this n-dimensional space, of course, is this one with this many zeros, right? So the total number of entries, of course, is n, right? So and then you also need to consider 0, 1 and then many zeros. Again, the total n number of entries of this column vectors is n, right? So you have n of these basis vectors because you are talking about a vector in the n-dimensional space. So, but regardless, is that you take this, right? So you ask yourself, so how does it transform? So if you know that, you just put that as the first column, right? And then you ask, how does this vector transform? If you don't know the result, right, write this as the second column of your matrix, and then so on. Right? So So in the end, okay, in the end, I have this general case, but as I said, we are not going to talk about this much. Okay. So now let's go to the next. Okay, so let's focus on our special cases. Okay, so is that the 2x2 case, right? So I'm going to talk about a few common examples of this linear transformation. So the first one is known as the scaling. Okay, what does it mean by scaling? Scaling, that means that you multiply everything by a factor, a scale factor that you choose, right? So, and that means what I have here is that if you take any vector, right? So x, y, And after the scaling, you will have a vector of a different length. Okay, so let's say if I scale it by 2, right? So then you can see that I have this transform vector to be longer, right? So the length is doubled, but this scaling does not change the direction of the vector itself. Right? So then you can see that the two vectors are pointing in the same direction. Right. So similarly, if I have another vector, right? So this blue vector, again, the scaling will give me this red vector. So again, double in length, and then direction unchanged. Okay. So of course, this kind of scaling is really trivial, right? To do, right? So you just need to multiply this column vector by a number k, right? So then that's it. So okay, so but if I really want to just write it in a matrix form, so then it will be a matrix that looks like this, right? So but again, the reason is because, right? So when I want to write down this matrix, right? So the as I said, I need to ask myself two questions. The first question is, how does 1, 0 transform, right? So this 1, 0. If you take the scaling, right, so it will become a vector that is, this is longer, right? So it will become k0, right? So because my scale factor is k. So similarly, right, so if you take a vector 0, 1, then the scaling, right, so will give you this vector 0k. So that's why this k0 will be the first column of my transformation matrix. And then this 0k will be my second column of my transformation matrix. Right? So this one is very easy. So the next example, okay, is so-called a reflection. So what it means is that suppose I have a vector here, right, this blue vector here, and then you see that my dashed line here, which is the symmetry axis. So suppose this is like the line that where I put a mirror on it, right? So if I want to look at the mirror reflection for this blue vector, right? So about this plane here, then what you get would be this red vector here, right? So this is a reflection. So then again, how do the reflection matrix is given by this, and how do we construct this? Right, so the way we construct it is again same thing, right? So we just ask ourselves two questions, right? So I want to look at this 1, 0. So 1, 0 after the reflection, what does it look like? Right, so it will become the vector over here, right? So and the angle between this green and this dashed line is theta, and that's why after the reflection, the angle between this purple and this dashed line is also theta, right? And let me draw it over here again, right? So then I have this to start with, and then I end up with this. And this angle, right? This angle, the total angle over here is 2 theta, right? So the reflection does not change the magnitude of the vector, right? So that's why I start with a magnitude 1, and then I end up with a magnitude 1. So then what is this vector here? So this vector really is that the x component of this vector is this one, right? So this is cosine 2 theta. And then the y component, of course, is this length here, which is sine 2 theta. So sine 2 theta. So that means 1, 0, after this reflection transformation, then what we have is cosine 2 theta and sine 2 theta. Right. So now similarly, right? So I need to know what happened to 0, 1. Right? This is my 0, 1. So, and I want to see the angle between this dashed line and my vector, right? So what is this? This angle is pi over 2 minus theta. Right? So after transformation, after the reflection, then the vector may be looking something like this. Right? This one. So this angle here, right? So again, will be pi divided by 2 minus theta. So then I want to find out the x and y component for this vector here. So then let me draw it over here again. Right, so this is my x-axis, and then I have a vector over here. And then I need to know this angle here. So this small angle here. So this small angle here, what is it? It's a pi divided by 2 minus theta. So this is pi divided by 2 minus 2 theta. And that's why, right? So the x component of this vector, of this reflected vector, is cosine pi divided by 2 minus 2 theta. And then the y component is minus sine pi over 2 minus 2 theta. And which is just equals to sine 2 theta and minus cosine 2 theta. Okay. So that's why you can see that, right? So the first column of the transformation matrix given by this, and then the second column of the transformation matrix given by this. So just some simple examples, right? So you just need to take the reflection matrix over here, and then consider how did you put your symmetry axis, right? So here, if I want to do reflection about the y-axis, so that means that then this is my symmetry axis, right? So this is my symmetry axis. So that means that I want to know the angle between my line here with the x-axis. So this is pi over 2. Right. So that means if you put pi over 2, theta equals pi over 2 into this matrix here, then you'll get this. Right. So in this case, it's really simple, right? So the difference is just that the reflected vector, right? So is compared with this original vector, is that the reflected vector has this minus x and y, right? So the x component, the x coordinate is flipped to the negative, right? And then the y component, y coordinate will remain unchanged. Right. So similarly, if I want to do reflection about the x-axis, right? So this time the theta is just 0. Then you can work it out to find out that this is your reflection matrix here. So and this time, of course, right? So the x coordinate not change. It's just that the y coordinate is go to negative. So finally, right? So if I do a reflection about this line, right? So then I need to know this angle here. So this angle here actually is right. So 90 degree plus 45 degree, right? So this is 3 pi divided by 4. Okay. So again, you put data equals 3 pi divided by 4, right? So into your matrix in the last slide, right? So you can get this result here. So the next example is known as the projection. The projection matrix is that I take a vector, I take this vector, but the projection, so first, for example, projection onto the x-axis means that I just keep the x component of this vector, right? So you can see that if I start with this blue vector, if I just keep the x component of my vector, then I'll end up with this red vector here. So then the original and the final vectors have the same x component, but then the final vector does not have y component. Same thing here, right? So then on the other hand, right, so if you want to do projection onto the y-axis, so that means that you're just going to keep the y component of your vector and then kill the x component, just like this. So again, how do we obtain this transformation matrix? Okay, it should be quite easy. So again, we consider two cases, right? So I ask, how does this 1, 0 transform? So the projection of this 1, 0 is 1, 0 itself, right? Because it does not have any y component to start with, right? So that means 1, 0 just give me back 1, 0. Right? So, and on the other hand, I want to ask, how does this 0, 1 transform? So this time, right, so the 0, 1 after transformation, it just becomes a point here, right? So the y component has to vanish, but it does not have any x component to start with, right? So then that means it will give 0, 0. So that's why your projection matrix onto the x-axis is given by this 1, 0 and 0, 0. So similarly, if you projection on the y-axis is 0, 0 and 0, 1. So, and then one more. Okay, so this is the one that I believe that you have or you will use quite often, is the rotation. Right? So rotation, what is it, right? So of course, it's just that if we start with a vector, blue vector, so rotation just means that this arrow here, right, just like on a clock, right? So it just rotates to another angle. Okay, so to this red vector here. So and here I'm considering a anti-clockwise rotation. Okay, an anti-clockwise rotation. So again, so how do we find out this transformation matrix, right? So same thing again, right? So in this picture, this blue vector already looks like 1, 0. So let me just call this. Let me just call this 1, 0. Okay. So you want to rotate this 1, 0, right? So what you have, right? So then you will have this vector here. So you will have this vector. So rotation does not change the length again, right? So then this length is still 1, and then so that's why this x component of this rotated vector, of course, is cosine theta, right? And then this y component is sine theta, and that's why this 1, 0 will give you cosine theta and then sine theta. So similarly, right, so if you consider this 0, 1, right, so then after rotation, it will be over here. Then you'll be able to find that this 0, 1 actually give you minus sine theta cosine theta. And that's how you construct the transformation matrix again. So again, just two simple examples, right? So pi over 4, right? So you just need to substitute this theta equals pi over 4 into this matrix, right? So then you get your rotation matrix. And if I want to rotate it by minus pi over 4, right? So nothing but just substitute minus pi over 4 into this matrix. Okay. So, but when you do a minus angle, then that means that your rotation is in the clockwise direction, right? Instead of in the anti-clockwise direction. Right? Anti-clockwise will refer to this positive angle. Right? So clockwise refer to this negative angle. So then let's take a look at the generalized case. Okay, so this time I'm considering a rotation in three-dimensional space. Okay, so rotation in three-dimensional space will be more complicated than the rotation in two-dimensional space, because when you talk about rotation in two-dimensional space, right? So you know that it's understood that the rotation axis is the axis that is pointing out of the paper, right? So it is just perpendicular to the XY plane. So that's the only choice that you can have, okay, for the 2D case. Okay. But for the 3D case, right? So in principle, right? So you can have infinitely many choice as your direction of your rotation axis, right? So, but here, if we just consider three special cases, is that I want to know the rotation about x-axis, the rotation about y-axis, and the rotation about z-axis. Okay, so how does it look like? Right. So then the rotation of this vector in the 3D space looks something like this, right? So let me first draw a circle like this. So then suppose my original vector is like this. Okay, so this circle is not a real object. It's just a circle that I draw somewhere above the XY plane, but it's parallel to the XY plane. Okay, so suppose the tip of my original vector touch a point of this circle, right? So after my rotation, right? So then my vector will be still touching the same circle, but at a different point. Right. So then this rotation, so where is the theta? So theta is this one, right? So this is the theta. So just like if my finger is pointing up is the z-axis, and this pen is the vector, right? So then the rotation about the z-axis is a rotation like this, right? So that's a rotation about the z-axis. So how do I construct a matrix, okay, for this rotation about the z-axis? Right? So here is a bit more complicated, because now you have this three basis vector to consider, but you can see that really the situation is essentially the same as what we had over here, right? So because again, we just need to consider the basis. What does the basis vector do, right? So we need to consider this one, which is x hat, right? So which is this time is 1, 0, 0. So you understand that after rotation, right? So it will be a vector that looks like this, still staying on the XY plane. And that is exactly given by this one. And then if you consider the rotation of this 0, 1, 0, right? So after rotation, right? So it will be something like that. But again, this rotated vector, and maybe I'm not drawing it very well, but this rotated blue vector is still lying on the XY plane, right? and that is given by this. So finally, right, so if you want to consider this one, right, the 001. So how does that rotation affect this? The rotation about the z-axis does not affect this vector at all, right? Because to begin with, this is already parallel to the z-axis. So that's why a rotation does not change this 001 at all, right? So that's why you have this. And this is how you construct this rotation vector about the z-axis, okay, for this 3D space. And same idea, right? So you'll be able to construct the rotation matrix about the x-axis and the y-axis. So in the previous few cases, right? So we have this situation where the geometric meaning is very common and clear, right? So the rotation, the reflection, and the scaling, these are all very common operations that we do, right? So, and of course, in general, right? So you can write down an arbitrary matrix and tell me that this is a transformation, right? So although that transformation, I might not be able to give you a very simple geometric description, but in any case, you can call that a transformation. Right? For example, I call this 2, 1/2, 1/2, 2 to be a transformation. Right? So, and in that case, what would happen? Right? So in that case, so suppose I have these couples of vectors to start with, then if you take this transformation, right? So each vectors will behave differently, right? So this vector here, let me just label it. So this vector number 1 here, right, will give me this vector here, right? So this vector number 2 here will give me this vector here. So number 3 here will give me this number 3 here. You can see that this is still some kind of transformation of a vector, but I just cannot give you a simple name or simple geometric description for it, right? But anyway, this is a transformation. And I will actually come back to this example later. And here you can see one thing is that if let's say if I consider if you consider number 2, but originally number 2 is pointing horizontally, right? So and then after transformation is pointing a little bit up. So it seems that if you want to describe it as a rotation, then it would be kind of a rotation in the anti-clockwise, right? So but now if you look at number 4, which is originally pointing down, right? So but after the transformation is still pointing down, but it's still a little bit to the left, right? So then that will be some kind of a rotation in the clockwise direction, right? So so then in these two cases, right? So you can see that the direction change in a different way. But if you look at number 1, actually, although the magnitude of number 1 also changed, but in fact the direction stay the same. Okay, in fact the direction of number 1 is remain unchanged under this transformation. And also look at number 3. Number 3 also the same thing, right? So the direction is actually not changed. Okay. So you can see that there are special vectors that under this transformation, okay, the direction is not changed. And these two vectors, as I will introduce later, are known as the eigenvectors, okay, of this transformation matrix. Okay. I'll get to that later. Okay. So then we can do transformations then we can undo it, right? So then that would be called the inverse transformation, right? So from V, I apply this transformation T to get to V prime, and then I apply this T inverse on this V prime to give me back V, right? So, and to do that, right, so basically what we do is an inverse matrix, right? So then the scaling, right? So the matrix looks like this, right? Then the inverse transformation for scaling, of course, geometrically is clear, right? So you multiply the length by a factor of k. Then if you want to undo it, then you multiply that scaled vector by a factor of 1 divided by k. So that's why I have this 1 divided by k here. And mathematically, right? So mathematically, as I said, this is the inverse matrix. So this A times this A inverse has to be an identity matrix. So reflection, right? Reflection, right? Geometrically, we know how to do the inverse, right? So if you reflect it once, right? So and then you just want to reflect it back, right? So to do that, what you do really is just that you take this data and then to minus data, then you get this inverse transformation for the reflection. But again, mathematically, as I said, right? So you can also just find the inverse of this matrix to get to the inverse transformation. Right. Finally, rotation. Right. So rotation, if I rotate it by angle anti-clockwise, then the inverse, of course, is to rotate it by the same angle but clockwise. Right. So that would be taking theta first and then taking minus theta, and then you get back to the same position. Right. So then you try to replace this theta by minus theta, you actually get this inverse transformation. Or mathematically, you just need to take the inverse of this matrix. So this one special case here is that if I actually take the orthogonal projection matrix, the inverse transformation does not exist. Mathematically, again, it's easy to understand because well, inverse does not exist, right? The inverse matrix of this matrix does not exist because the determinant is 0. And geometrically, it's also not difficult to understand, right? So if I just tell you the projected vector of the original vector, you have lost the information of the y component of the original vector, right? So that's why if I give you the projected vector, it's impossible for you to tell me what the original vector is, right? Because you don't know the y component. And okay, at this point, okay, maybe let's take a break. Okay, let's take a 10-minute break. We'll come back at 12:25. Okay, so let's continue. Okay, so just now we are talking about transformation and then inverse transformation. So now let's talk about two transformations that we just do one first and then followed by the other. Right. So that means that if I have a vector v, and then I do a first transformation which I call T1, right? So then I'll get v prime, and then this v prime is equal to this A1 v, right? So this A1 is the transformation matrix for the T1. So then taking this v prime, I'm going to do another transformation, right? So this T2, and then at the end, I get this v double prime. Right? And this v double prime, right? So again, I can represent it as this A2 v prime. Right? This A2 is the transformation matrix for this T2. And this A2V prime is equals to A2 times this one, right? So A2 times A1 times this V. So that means if I have two transformation, one followed by the other, then that is the same as multiplying the product of the two matrix, okay, to my vector V. So example here, right? So suppose I start with this vector, this blue vector, and then I do a rotation, and then get this red vector here. After that, I do an enlargement or scaling, right? So to make the magnitude of this red vector bigger, right? So and then at the end, I got this green vector here. So then from blue to red to green, right? So then that would be the same as, right? So multiplying this matrix first to this vector first, and then multiply the second matrix to this whole thing here. Right? So or right, I would say that from this red to green is the same as multiplying the product of these two matrices, right? So to my original vector. So so now we have a product of two matrices, and then now we want to examine, okay, whether applying this A2 first and then A1 will be equals to applying A1 first and then A2. Right? So this first order here is the same as what I showed you in the last slide. Right? So I do rotation first and then do this enlargement or scaling, right? So to get to here. And then if I switch the order, so that means that I do the scaling first and then I do the rotation. You can see that in this example here, orders doesn't matter, right? So the two orders give you the same final green vector. So and mathematically, that's because this A2, A1, which is this matrix, is equals to this A1, A2, which is this matrix. However, right, so the order of operations in other case will actually affect the result, right? So in this example, this time I do rotation first and then a projection, right? So from red, from this blue to this red, and then from this red to this green. Okay. In this case, right, so from red to from blue all the way to green is represented by this matrix here. Right. But if I reverse the order, right, so first of all, I do projection first and then do rotation. Then I will get a vector that looks like this, okay, which is not the same as the first case here. This is easy to understand, right? Because projection will make your final vector to be lying on the x-axis, right? But if you do rotation the last, right, projection the first, and then your final vector won't be lying on the x-axis. So clearly, right, so these two cases not the same. So then that means, right, so we now see that this A1, A2, okay, may not be always equal to this A2, A1. And that depends on whether the two matrices are commute. Okay. So the definition of commute for two matrices is that if AB equals BA, then I'll say that these two matrices commute. And here are some examples. Okay, so but I won't talk about the proof. Okay, but the first two are actually very easy. Okay, so the identity matrix commutes with all matrices. Of course, it is the case, right? So the identity matrix is just the 1, 0, 0, 1. And the other is that every diagonal matrix commutes with all other diagonal matrices. In fact, this is also not difficult to prove. You can actually try yourself. And also, if the product of the two symmetric matrices is symmetric, then the two matrices must commute. And here, I'll introduce a thing that is so-called a commutator, okay, which you will see again when you learn quantum physics. Okay, so the commutator of two matrices, okay, or two operators, as you see in quantum mechanics course, is that I'll use this square bracket to represent. Okay, so this commutator of this A and B, right? So written like this, and by definition is equals to AB minus BA. Okay. And you can see that, right? So if this commutator is 0, so then that's equivalent to say that AB equals BA, right? So then that means that A and B are commute. So now I want to talk about the so-called the eigenvectors, okay, and also eigenvalue of transformation matrix. Okay. So you may still remember the example I talked about before the break, right? So is that if I consider this transformation, right, so you can see that there are two special vectors which remains their same direction after the transformation, and these are known as the eigenvector. Okay. So let me define it more formally, right? So right, so I have this linear transformation, right? So from A times V, right? So equals to this V prime. Okay. So as I mentioned already, right, so the transformation of a vector, right, so would involve a change in magnitudes and or directions, right? So in general, right, so both can change. Okay. And the change experienced by different input vectors, okay, are different, just like the example I showed you. Right? And for some V, right, so the transformed vector V prime is just parallel or anti-parallel to V. So what it means is that it stay in the same direction. Parallels, that means the V prime and V point to the same direction. Right? Anti-parallel just means that the V prime and V point exactly in the opposite direction, but still they stay on the same line. So that's what it means. Right? And then, so the definition of eigenvectors is that it's a vector V, okay, which is parallel or anti-parallel, okay, to its own transformed vector V prime. So, and mathematically, okay, so that's not the definition there, but here is another example here. Okay, so is that if I talk about reflection, I talk about reflection of about y-axis. Okay, so what are the eigenvectors? Right, so the eigenvectors, remember, right, so as I told you the definition already, is that after transformation, right, so the direction has to be remain unchanged, or it just go to the exact opposite direction. Right, so then from this reflection case, you can clearly see that one of the possibility is this one. Right, if you start with this green vector, right, so after reflection is still the green vector. because I'm talking about reflection about the y-axis. Right, so then this green vector is one of the eigenvectors. Right. After transformation, direction not changed. So another eigenvector is actually the one that is lie on the x-axis. Okay. So this purple one. If I start with this purple one, after reflection, what it becomes is a vector that is pointing to the negative x direction. Direction is changed, but it still stay on the same line. So direction exactly becomes opposite. And that is also considered to be an eigenvector. So that's why in this case, right, the reflection is 1, 0, and 0, 1 are two eigenvectors of this reflection matrix. Of course, you can say that 2, 0 also eigenvector, 3, 0 also eigenvector. Right. Similarly, if I just say 0, 1 or 0, 2, 0, 3, 0, 4, they are also eigenvector. Right. But at the end of the day, so that's why here I will say that's 1, 0 and 0, 1 and their scalar multiples. But at the end of the day, when we say the eigenvectors for a matrix, we'll just we won't say that there are infinitely many of them. We'll just list out the set that are linearly independent. Right. So if I list out this set, right, so 1, 0, and 0, 1, these are the two linearly independent vectors that is sufficient to represent, okay, so the eigenvectors of this matrix. Okay. Or you can say, okay, 2, 0, and 0, 2, that's fine also. Okay. But you won't say that it's 1, 0, 2, 0, 3, 0, and then 0, 1, 0, 2, and so on. You won't tell me that there are 6 eigenvectors. Okay. You will just tell me that there are 2 eigenvectors. So here is another example. Okay, so is that the scaling or this enlargement is that if I have this xy, right? So after transformation, it just get longer. Okay, direction not changed. Then in this case, what are the eigenvectors? Okay, for this matrix. In this case, really, no matter what you input, right? So the output will still be parallel to the input. Right? So then this time, you say that any vectors, so any vectors in the xy plane, right? So can be eigenvectors of this scaling or this enlargement matrix. But again, at the end, you will try to just use a set of vectors, okay, so to represent kind of all of them, right? So here you can still, I will still say that this 1, 0 and 0, 1, okay, and their linear combination to be the eigenvectors of this matrix here. So this case actually is quite different than this case. So here, really, 1, 0 and 0, 1 only. You cannot say that the linear combination of these two vectors are still eigenvectors. That's not true, right? So if you add 1, 0 to 0, 1, then you get 1, 1. Then 1, 1 won't be an eigenvector of this matrix. However, here is different. Okay, so it's actually 1, 0 and 0, 1, and then their linear combination. Okay, so this is basically a way to say that any vectors in this two-dimensional space are eigenvectors. Okay, so example 3 is the case where I don't have any eigenvector. Just think of rotation. Okay, rotation, whenever you put in a vector, it doesn't matter where it points to, after rotation, its direction has to change, right? So that in that case, you can never find a vector that is parallel to its transformed vector. Of course, you can think of special case, right? If theta is 0 or if theta is exactly pi, then that's possible. Okay, but in general, let's say theta is not 0, is not pi, then you don't have any eigenvector. Okay. Or you see that I use a bracket real, that means at least there are no so-called real eigenvector. Okay, if you actually allow complex numbers to be in the picture, okay, you can actually find vectors, but the entry contains a complex number. But I'll show you how it works later. Okay, but here you can see 3 different examples. Yeah. So finally, let's do one more example here. Is that if I do again a rotation in 3 dimensions. Okay. So this time, again, similar to the last example, is that whenever I put in a vector, so you get rotated, right? So then you cannot get real eigenvectors, right? So but here you always can find an exception, right? Because if your input vector by itself is already parallel to your rotation axis, so that means that vectors won't be affected by rotation at all. Right, so then that vector, of course, at least is a real eigenvector. Right. So then here, right, so if you have this rotation about the x-axis, okay, if you have this rotation about the x-axis, yeah, I think this is the typo here, this is y-axis. If you have rotation about the x-axis, then the x hat itself will be an eigenvector. Right? If you have a rotation about the y-axis, then this y hat itself is an eigenvector. Okay. Rotation about z-axis, then the z hat itself will be an eigenvector. Okay. So now let's look at a systematic way to actually find out the eigenvectors. So in the previous examples, basically, I'm just kind of relying on this geometric picture, right? So to figure out the eigenvectors or to determine whether they are eigenvectors or not. But here, let's look at a systematic mathematical procedure on how to look for the eigenvectors for any transformation matrix. Okay. So in general, okay, remember that we are looking for this linear transformation, okay, from n-dimensional space to n-dimensional space. Okay. So when we talk about eigenvectors, okay, so the before and after, okay, the dimension have to be the same. Okay. So as I said already, right? So the eigenvectors is the vector that after transformation, it is parallel or anti-parallel to the untransformed vector. Or that means the transformed vector v prime can be written as the original vector v times some scalar number. Right. So then that's if you have an eigenvector, it can always be expressed like this. Right. And this lambda, we don't know what it is yet, but as long as it's a scalar, it's okay. Right. It can be 1, 2, 100, it can be -10. Okay, it can be positive, negative. Right. As long as it's just a scalar, then it's fine. Okay. So then, in fact, this lambda also has a name. Okay, this lambda is known as the eigenvalue of the matrix A. Okay. And in fact, if you have an n by n matrix, That means if you're considering a linear transformation from n-dimensional space to n-dimensional space, then you will find n eigenvalues. So n values for this lambda. However, some of them may be repeated. Okay, as you will see why in a minute. So then what do we need to do here, right? So we need to find out the v prime, okay, and in fact, to find out v prime, we first need to find out lambda. Okay. We first need to find out lambda. Okay. So this is the requirement. Okay. So we are looking for some v such that after the transformation is just given by lambda times v. Okay. So first, let's try to find out lambda. So this system itself, if I put the right-hand side also to the left-hand side, right? So then I'll have this system, right? So A minus lambda I is the identity matrix. Okay, so this system is equivalent to A minus lambda I, okay, multiplied by this V equals 0. Okay. So this system of then this is really becomes a system of linear equations, and in fact this is a homogeneous system of linear equations, right? As I have introduced in the last part of the chapter. Okay. So now here is the key steps. Okay, so listen carefully. So now I have this homogeneous system. Okay, so we know that homogeneous systems, right? So always have solution, right? So either just have one solution or infinitely many solutions. Right? So if this linear system only has one solution, so that means that is the so-called zero solution or trivial solution. So that means V is just a zero vector. But that's not what we want, right? So zero vector is not considered to be an eigenvector. Okay. So when we talk about eigenvector, it has to be a vector that has a finite length. Okay. So that means we want, okay, we hope that this homogeneous system has non-zero solution. And then that means we require that the determinant of this matrix has to be 0. Okay. So then if you set this determinant to be 0, and then you expand this determinant, you'll be able to find that this is an nth order polynomial equation in lambda. Okay. So, right, so if you have an n by n matrix A, okay, if you have this determinant to be expanded out, right, so you find that it's lambda to the n plus something times lambda to the n minus 1 and so on equals 0. So then with that polynomial in lambda, then you need to find the roots of this polynomial to obtain the different values of lambda. And these different values of these roots are really is the eigenvalue. Okay. So if you have an nth order polynomials, right? So the algebra tells us that you are guaranteed to have n roots. Okay. So that means that you are guaranteed to have n values of the eigenvalue lambda. However, you also know that some of the roots can be repeated root. Right. So, but anyway, I will still call that n roots. Right. So now suppose you have solved the polynomial. Okay, you have solved the polynomial and then find out the lambdas already. And then you just substitute each lambda, okay, one by one back to the system. Okay. So suppose I substitute the first root of this polynomial, okay, to this back to this system. Okay. And then what I can do is to actually solve for a V. Right? So before, when we are at this step, right, before we did not know what lambda is. Right? So now we know. And then so that's why we substitute that known value of lambda back to this system, and then we solve for V. Okay. And so you can at most, at the end, get n linearly independent eigenvector. So let's try to do an example. Okay, so to understand how the procedure works. So again, we start with this 2x2 example. So what is the first step? The first step is to look at the determinant of A minus lambda I. So A is this, right? So remember what is lambda I? Lambda I is this. Okay. So that's why the determinant of this A minus lambda I would be this one, right? So you can see that the diagonal terms, I'll need to have this minus lambda. So you expand this determinant, okay? So you obtain a quadratic polynomial, okay, for the lambda. So, and then you need to set this one, right? So equals 0. And then if you have that, then this becomes a quadratic equation. And in this case, right, so the lambda can be either 2 or 8. Right? So these two are the roots of this quadratic equation here. So that means the eigenvalues of A is 2 and 8. So after you obtain the eigenvalues, okay, so you will substitute this one of them, or substitute them one by one back to the system, and then solve for V. So substitute the eigenvalues back to the system. Okay. So here, okay, so this x1, x2 is the V vector. Okay. So instead of using x and y, so here I just denote it by x1 and x2. Okay. So I'm missing a lambda here. So case by case, right? So first case, lambda equals 2. So lambda equals 2, that means it's the A times V equals 2 times V. So you just go ahead and solve this system, and then it gives these two linear equations. Okay. And of course, you will find that you always will find that you have infinitely many solutions, right? Because this is the homogeneous system, right? And then the lambda we found is such that the system itself has infinitely many solutions, right? So then that's why whenever you solve this system, you'll find infinitely many solutions. And if you have this two equations further simplified, you'll find that these two equations is just equivalent to x1 plus x2 equals 0. So then you have infinitely many possibilities. Right? If x1 is 1, then x2 has to be -1. If x1 is 2, then x2 has to be -2. Right? Infinitely many pairs of x1 and x2 can satisfy. But at the end, so if I just call this x2 as a free parameter k, then this x1 it just has to be minus k. And remember that we are not interested in the 0 solution. So k is not 0. So and therefore, this vector x is okay. So rotation difference. So this is x. Okay. So then this vector x is really minus 1, 1 times any scalar k. So then this is one eigenvector. So I'll just call this minus 1 the eigenvector, okay, which is corresponding to lambda equals 2. So then for the other case, so lambda equals 8, we just do the same thing. Just do the same thing, is that we substitute this back to the system. Okay. And then this time, you'll find that minus x1 plus x2 equals 0. Okay. Instead of x1 plus x2 equals 0. And again, you can see that infinitely many possibility, right? So here I'll just call this x1 equals x2 equals to some 3-parameter k. Okay. Then this time the eigenvector is 1, 1. Okay, multiplied by any parameter k. Okay. So here you can see 2 eigenvectors. Okay, each one corresponds to their own eigenvalue. Okay. So this is the standard procedures. Okay, I would like to have you try one time, okay, by yourself. Okay, so try, I want to go back to this example. Try this one. Okay, so I want you to find the eigenvalues and eigenvector of this matrix here. Okay. Just try to do it once by yourself. Okay, so to make sure that you know the procedure. Okay. Okay, so let's try to see how to do it. Okay, so I'll just call this matrix A. Right, so this is my vector V. So my system, I'm looking for this system here. So A minus lambda I times V equals 0. Right. Looking for non-zero V vector that satisfy this system. Right. So that's why I require A minus lambda I determinant to be 0. Right. So then this A is 2, 1/2, 1/2, 2. So minus this lambda 0, 0 lambda. Right, the determinant of this. The determinant of this is equals to 2 minus lambda 1/2, 1/2, 2 minus lambda. This one, if you just expand the determinant, right? So then you get 2 minus lambda square minus 1 divided by 4. And then I want this to be 0. Right. So that means 2 minus lambda is equals to plus or minus 1/2. So that means lambda equals 5 divided by 2 or 3 divided by 2. So then I need to take care of each case one by one, right? So then for lambda equals 5 divided by 2, then what I'm going to consider, I'm going back to consider this system here. Right. So then what I have is 2 minus 5 divided by 2 x plus 1/2 y equals 0. And 1/2 x plus 2 minus 5 divided by 2 y equals 0. Right, so this system becomes this one. So then if you try to simplify them, okay, so you'll find that it's equivalent to this one. So the first equation is saying the same thing as the second equation, actually. So that means that it really just tells you that x equals y. And if you pick a free parameter for this x, and we call this k, then y has also be k, has also to be the k, the same k. And that means the eigenvectors would be k times 1, 1. So then this is the eigenvector corresponding to this lambda equals 5 divided by 2. So similarly, so if you work on this lambda equals the other value, 3 divided by 2, then what you have is you'll find that this will be equal to k times 1 minus 1. So two eigenvectors, 1, 1, and 1 minus 1. Now I want you to again look back to this picture here. Okay. So in fact, this is the 1, 1. Okay. And now you can see that this is the eigenvector, right? So as I mentioned before already, so before transformation, pointing to this direction. After transformation, also pointing to the same direction. However, after transformation, okay, so the length become longer. In fact, it's longer is multiplied by this factor. Okay. This is the eigenvalue. So then the second eigenvector, right? So 1 minus 1. So which is this one over here. Okay. So this is 1 minus 1. So after transformation, stay in the same direction, but again, it's get longer. Becomes this one. Okay. So, and again, of course, so any vectors that is parallel to this line, right? So will be the eigenvectors, right? So any vectors parallel to this line will also be eigenvectors. But at the end, okay, you just use these two to represent them. So the procedure should be standard, okay? So, but later, there's just one thing that you need to be careful is when we have the repeated roots, okay? So in the first two examples that I just talked about, so you get two different value of lambda, so two different eigenvalues. Okay. When I will soon talk about the case if I have two eigenvalues to be the same as each other. But so actually, so let me go to this page and just quickly go through these examples here. Right, so reflection matrix, scaling matrix, rotation matrix. Right, so from geometric argument, I already told you the answer. Right, so you know that the reflection matrix, the eigenvectors is 1, 0, and 0, 1. Just from geometrical argument. Right, so here, try to apply the procedures that we just learned to verify that this is indeed the case. Right, so reflection matrix. So reflection matrix here, well, I should specify, but what I'm going to talk about is reflection about the y-axis. Just take this special case. Right, so I'm looking for eigenvalue and eigenvector of this matrix. So I need to do this determinant. I need to do this determinant. This determinant is equals to, if I expand it, it's just 1 minus lambda times minus 1 minus lambda has to be equal to 0. And that means it will be either plus or minus 1. And if you go ahead and put this lambdas back to the system, okay, so you'll be find that the lambda equals 1. Okay, so then the system becomes 1 minus 1 x plus 0 y equals 0. And 0 x plus minus 1 minus y equals 0. From here, what it tells you is really, first equation just tells you nothing but 0 equals 0. Right, and then the second equation tells you minus 2y equals 0. So that means y has to be equal to 0, and x can be anything. Right, so x can be anything. Let me again call that k, and then y has to be 0. So that means for lambda equals 1, your eigenvector is k times 1, 0. So, and of course, that's just means 1, 0. And similarly, if you go for this lambda equals minus 1, then you'll find that no need to repeat the whole procedure. The eigenvector would be k times 0, 1. So let me see. Did I make a mistake here? Oh, this matrix is correct, but okay, so this is a reflection about the x-axis. Okay, so not a reflection about y-axis. Right, so this is a reflection about the x-axis. So then this is the first case, right? So it verified our geometric argument here. So now the second case, the scaling matrix. So let me. if I consider the second case, the scaling matrix, so I have this kind of matrix. And I want to find, again, the eigenvalue and eigenvector of it. Okay, then what I have is k minus lambda 0, 0, k minus lambda. Right, so this one is just k minus lambda square equals 0. So that means lambda equals k. So this is a repeated root. So if we substitute this back to the system, actually what you find is 0 minus 0x plus 0 times y equals 0. And then 0 times x plus 0 times y equals 0. And really, it tells you nothing, right? So no any requirement for the x and y, right? So that means that x can be x can be anything, right? So any free parameter. So I will just call this C1, and then also y can be anything also, and I call this C2. So C1 and C2 are unrelated. Right. So then basically, then that means you can write your eigenvectors, right? So like this, right? So and C1, C2, anything. Right. So, but again, in this case, when we see something like this, we'll still try to find a pair of linearly independent eigenvectors to represent this result. Right. So for example, in this case, I can write it this way, right? C1, 1, 0 plus C2, 0, 1. Right. So then I will say that 1, 0 and 0, 1, okay, so are the pairs of the eigenvectors that we choose. And really, any other linear any linear combinations of this 1, 0 and 0, 1 will also work. Right. So if you don't like this 1, 0 and 0, 1 to be your answer, right? So you can say that like 1 minus 1 and then 1, 1 to be your answer. This also will form a basis set, okay, that describe any vectors, okay, so on the xy plane. Okay. And also, if you don't like this, right, so you can also say that 1, 0 and 1, 1, okay, to be the answer. Okay. So these two are still linearly independent, right? So any vectors that looks like this can still be written as a linear combination of these two vectors. So there are many choices that you can pick, right? So you can either, this is your first choice, right? So first set of choice, and this is your second set of choice, right? So and then this is your third set of choice. Okay, you can find many more. And at the end of the day, you just give me any set and you are correct, right? So, but usually, right? So usually, to make it convenient, right? So we will make the set that looks like the two vectors are orthogonal to each other, right? Or perpendicular to each other. If you pick this set, right? So you can see that this one is nice. 1, 0 and 0, 1, right? So they are orthogonal, they are perpendicular. So finally, okay, so let me also talk about the rotation matrix. Okay. Rotation matrix is the case that I just told you that does not have eigenvectors. Okay. Geometrically, you understand why. Okay, but mathematically, okay, what happened? Right, so for rotation matrix, right? So I require this cosine theta minus lambda, okay, minus sine theta, and sine theta, cosine theta minus lambda. So I'm looking for this determinant. Right? So this determinant, if you expand it, you'll have cosine theta minus lambda square plus sine square theta, and it's equals to 0. Okay. So and that means cosine theta minus lambda is equals to plus or minus I times sine theta. Right. So I just put the sine square theta to the right hand side and then take square root of both sides. So then that means lambda is equal to cosine theta plus or minus I sine theta. It's a complex number. Cannot find any real number that satisfies this equation. Okay. So, and if you allow complex numbers to be in the game, then of course you can still substitute this lambda value back to your system of equations and then solve that, right? It's just that at the end, the solutions that you get for the so-called eigenvectors will contain complex number as well. And that's not the case that we will really discuss. Okay, so but just that mathematically, right, so you can still get eigenvectors if you allow complex numbers. But just that, well, geometrically, so you cannot really draw anything, right? So in the real space. Okay, so I think I have to stop for today. Okay, so we'll continue on Wednesday. So remember that the midterm is on next Monday.